In this tutorial, I will explain what the RAK831 Pilot Gateway is, how to configure it, and how you can register this gateway with the Things network. This video is sponsored by RAK. Rakwireless Technology, also known as RAK, was established in June 2014 and is based in Shenzhen, China. RAK's main focus is developing and supplying advanced IoT technology and services. Here are some interesting RAK links: their website, their documentation section, their online shop, and their support center. This presentation can be found at this link. All my LoRaWAN tutorials and presentations can be found at this link. There are many different gateways. One of them is the RAK831 Pilot Gateway. This gateway is designed for indoor usage and supports the LoRaWAN 1.0.2 protocol. It is ideal for prototyping, proof of concept demonstration, or for evaluation purposes. The RAK831 Pilot Gateway is a fully assembled gateway with an aluminum housing and is shipped with a micro SD card with all software pre-installed. Instead of the RAK831 Pilot Gateway, you can also buy a LoRaWAN Gateway developer kit and assemble the gateway yourself, but without the aluminum housing, thus reducing the price. The RAK831 Pilot Gateway can be purchased at the RAK online shop. The RAK831 Pilot Gateway supports the following frequency ranges. Check out the RAK documentation section for more technical specifications. The RAK831 Pilot Gateway consists of a Raspberry Pi 3 Model B+, a converter board with a GPS module U-Blocks Max 7Q, a RAK831 LoRa concentrator, an aluminum housing with the top cover serving as a heatsink. The housing size, depth, width and height is 69 by 92 by 54 mm. A power adapter 5V 2 amperes with micro USB, and the cable length is 115 cm. An antenna with the correct frequency for the LoRa radio, a GPS antenna and the cable length is 150 cm, and a micro SD card. The storage size is 16 GB class 10 with pre-installed software. Please note, I have noticed that RAK makes improvement to their products. Your RAK831 Pilot Gateway components may deviate from the one shown in this tutorial. Aluminum housing, bottom plate, top cover serving as a heatsink, thermal gap filler, Raspberry Pi 3 Model B+, converter board, GPS module U-Blocks Max 7Q, GPS antenna connector, RAK831 LoRa concentrator, LoRa antenna connector, LoRa antenna, IPEX connector, micro SD card with pre-installed software, power adapter output 5V 2 ampere with micro USB, GPS antenna. I have disassembled the RAK831 Pilot Gateway. Let's put it back again. The RAK831 concentrator uses a Semtech SX1301 chip and is able to receive up to 8 LoRa packets simultaneously and can send with different spreading factors on different channels. The concentrator is the radio communication module which receives and transmits radio messages. The converter board with the GPS module routes the signal between the Raspberry Pi and the RAK831 concentrator. This is done through these SPI buses. An SPI bus is used to send data between microcontroller and its peripherals, in this case sending data to and from the Raspberry Pi and the RAK831 concentrator via the converter board. Please note, SPI is already enabled in the installed Raspbian operating system. The Raspberry Pi processes these radio messages as well as protocol-related tasks and send the processed data to a LoRaWAN server, for example, the Things Network server. Here's a complete overview. End devices transmit sensor data to the RAK831 Pilot Gateway. The RAK831 concentrator board receives these signals, and these signals are routed to the Raspberry Pi through the converter board. The Raspberry Pi processes these radio messages, and the Raspberry Pi sends these processed data to a LoRaWAN server, for example, the Things Network. Later in my presentation, I will explain the purpose of the GPS module. The RAK831 Pilot Gateway is a fully assembled gateway and needs to be configured before it can be used. All software are already installed on the microSD card. Insert the micro SD card into the Raspberry Pi. Connect the LoRa antenna to the gateway. Never power up the gateway without the LoRa antenna. Otherwise, this can cause damage to your gateway. You do not need to connect the GPS antenna because GPS is by default disabled. I recommend not to connect the GPS antenna. I will explain this later. Connect the gateway to a router using an Ethernet cable. The Ethernet cable is not included. So connect your gateway to your router using an Ethernet cable. Then power up the gateway using the included power adapter. Do not use a power adapter with less than 2 ampere output. The gateway has the hostname TTN-gateway. There are several methods to get the gateway IP address. I will only demonstrate 3. The first method uses the router devices list. Open a browser and navigate to your router's IP address. The IP address is usually printed on a label on your router or check your router's manual. To access your router's configuration interface, you need its username and password. Check your router's manual. Locate the gateway, TTN-gateway, and write down its IP address. I've opened a browser and entered my router's IP address. This IP address may differ for your situation. In the router configuration, locate the TTN-gateway and find its IP address. For example, this is my IP address. The second method to get the gateway IP address is resolving the hostname.local with multicast DNS. On Raspbian, multicast DNS is supported out of the box by the Avahi service. If your computer supports multicast DNS, you can reach your gateway by using its hostname and the .local suffix. Open a terminal and enter command ping ttn-gateway.local and you will see the gateway IP address. If your computer does not support multicast DNS, install the Net Analyzer app, which is available for iOS and Android, on your mobile. Select the ping option and enter ttn-gateway.local. You will see the gateway IP address. If both methods does not work, try method 3. Connect a monitor using an HDMI cable and connect a USB keyboard to your gateway. In the monitor, you will see the login prompt. The default username is Pi and the password is Raspberry. Note, the Pi password may have changed to this password in the shipped microSD card. Next, log in with the above-mentioned credentials. Enter command hostname -I. The gateway IP address will be shown. On Linux and Mac, the SSH command can be used to access the Raspberry Pi. On Windows 10, SSH can be used, or instead use PuTTY. To enable SSH functionality on the Windows 10 PowerShell, open Settings, view the apps, go to the Manage Optional Features, click Add a Feature, select Open SSH Client, wait and then reboot. Unfortunately, I cannot demonstrate this because I do not own a Windows 10 computer. Now let's access the Raspberry Pi. Enter this command. Pi is the default username. And enter your gateway IP address. The default password is Raspberry. But it is possible that the default password Raspberry is changed to 1111-1111 in the shipped microSD card. Are you sure you want to continue? Enter yes. Enter the password and press enter. Open the Raspberry Pi software configuration tool, enter this command. Now let's change the user password. It is recommended that you change your password for security reasons. Select the first option and press the enter key. Enter my new password. Retype my password. And my password is changed. You can change your language and regional settings. Select the fourth option. Select Change Locale. Press the Enter key. And now you can change your locale settings. I live in the Netherlands, so I select this option. Press the spacebar and press the Enter key. Next, you can select the default locale for the system environment. Then press the right arrow key. and then press the Enter key. But for this video, I will not change my locale settings. I am back in the Raspberry Pi Software Configuration Tool main menu. I again select Localization Options, and I'm now going to change my time zone. My geographic area is Europe. My time zone is Amsterdam, and it is changed. Open a new terminal and access the Raspberry Pi, and enter this command. As you can see, my micro SD card is 16 gigabytes, which almost matches this size. But if this size is significantly smaller than your micro SD card size, you need to expand the file system on the micro SD card. Select Advanced Options. Select Expand File System. Unfortunately, I have already expanded my file system earlier. Press the Enter key. Press the right arrow key and select Finish. And select Yes. Press Enter. Again, access the Raspberry Pi. Log in with your new password. Check the disk space. And check if the size is changed. Check the time zone. In my case, this is correct. To register your gateway with the Things network, you need its gateway AUI. Once a gateway AUI is registered with the Things network, it cannot be used by someone else. The gateway AUI can be any random 8 bytes number, but it is recommended that the gateway AUI is based on the gateway MAC address. A MAC address is a hard-coded identification number which is assigned to your network interface card. The Raspberry Pi 3 has an Ethernet port and built-in Wi-Fi. Each network interface, Ethernet and Wi-Fi, has its own MAC address. ETH0 is the name of the first Ethernet interface. WLAN 0 is the name of the first wireless interface. If the gateway is connected to a router using the Ethernet cable, the ETH0 network interface is used. To get the ETH0 network interface MAC address, enter this command. If the gateway is connected to a router using Wi-Fi, the WLAN 0 network interface is used. To get the WLAN 0 network interface MAC address, enter this command. Please note, Wi-Fi is by default disabled in the RAK831 Pilot Gateway. Enter this command to get the ETH0 network interface MAC address. This is the MAC address. By the way, all Raspberry Pis have MAC addresses which starts with B827EB. Enter this command. And this is the WLAN 0 MAC address. As you can see over here, Wi-Fi is disabled. So I will use this MAC address. Again, here is the MAC address. It consists of 1, 2, 3, 4, 5, 6 bytes. Insert these 2 bytes after the third byte. So this is the first, second, and third byte. And I'm inserting these 2 bytes in here. Remove all colons, as you can see over here. Change to uppercase, as you can see over here. And this is now our gateway AUI. Write down the gateway AUI. You will need it later when registering the gateway with the Things Network console. The gateway is shipped with a micro SD card with the following software pre-installed. The Raspbian Stretch Lite. You can find this software at this location. The Semtech LoRa library version 5.0.1. You can find this software at this location. And it is installed in this folder. And finally, the Semtech UDP Packet Forwarder version 4.0.1. You can find this software at this location, and it is installed in this folder. In case the Semtech LoRa library and Semtech UDP Packet Forwarder are installed in 2 different folders, for example, in this folder and in this folder, then always use the one installed in this folder and ignore the other. Note, Instead of the Semtech UDP packet forwarder, the RAK831 Pilot Gateway can also work with other packet forwarders, but that is a subject for another video. Raspbian is the operating system which runs on the Raspberry Pi. To check which Raspbian release is installed, enter this command. So Raspbian version 9, named Stretch, is installed. Now let's check if a Raspbian Lite version is installed, which means no desktop. To verify if Raspberry Pi desktop is installed or not, check for package Raspberry Pi UI mods. The Raspberry Pi desktop requires this package. Enter this command and press enter. This means that Raspbian Lite is installed. The Semtech LoRa library contains drivers to be used in gateways using a concentrator board based on Semtech SX1301 multi-channel modem and SX1257 or SX1255 RF transceivers. The Semtech UDP packet forwarder is a program running on the host of a LoRa gateway, in my case the Raspberry Pi, that forwards RF packets received by the concentrator to a LoRaWAN server through an IP UDP link. The packet forwarder can also transmit RF packets which are sent by the LoRaWAN server. In this tutorial, the gateway will be connected to the Things Network server. A regional global config JSON file is needed, which can be downloaded from this location. This regional configuration file sets the frequencies which applies to a specific region, and it also sets the Things Network server address. Depending on the region your gateway will operate in, download the correct regional global config JSON file. This is the address where you can download the regional global config.json file. If your gateway operates in Europe, you download this file. If your gateway operates in China, you download this file. If your gateway operates in the United States, you download this file, etc. Let's open the EU global configuration JSON file. Here you can see the frequencies which applies to this specific region. And you can also see the Things Network server address and its ports. If the downloaded regional global config JSON file contains the LBT_CFG key, as you can see over here, then change the enable value from true to false. This will disable the listen before talk feature. Let's open this file. As you can see, LBT_CFG, you have to change the enable value to false. Open this file. There is no LBT_CFG key. You can connect the gateway to another LoRaWAN server instead of the Things Network server, for example, LoRaServer.io. But additional changes need to be made to the regional global config JSON file. How this is done, see this link. Go to this Raspberry Pi folder. This folder contains this file. Rename this file. My gateway operates in the Netherlands, so I am downloading this JSON file. After the file is downloaded, rename this file to global_conf.json. Reboot the Raspberry Pi. Enter this command and press enter. Log into the Raspberry Pi. Check the TTN gateway server status by entering this command. Press enter. There are no errors, and you can see GPS is disabled. For more logging information, go to this folder. In the syslog file, you can find interesting loggings. The RAK831 Pilot Gateway is shipped with a converter board with a u-blox MAC7Q GPS module soldered to it and a GPS antenna. The GPS module is connected via a UART or serial port to the Raspberry Pi. GPS satellites broadcast navigational messages to Earth, which contains very accurate timestamps and their position. The Gateway GPS module receives these navigational messages. With this information, the GPS module calculates its position on Earth. The GPS module can use these accurate timestamps to create a PPS signal. PPS stands for pulse per second, that is used for timing or synchronization purposes. Every LoRaWAN gateway with a GPS module generates the same synchronized PPS signal. If we have 3 gateways with GPS modules, they each generate the same synchronized PPS signal, as you can see over here. A gateway PPS signal is used to create time-synchronized beacons, which are sent to Class B end devices. As explained in Tutorial 4, Class B devices opens extra receive slots at scheduled times in addition to Class A's random receive slots. In order for the end device to open its receive slots at scheduled times, it requires a time-synchronized beacon. This allows the gateway to know when the node is listening. The RAK831 Pilot Gateway has a GPS module, but it is disabled. This is done because Class B functionality is not implemented yet in LoRaWAN servers, such as the Things Network servers. This video is made in January 2019. It is therefore not useful yet to enable GPS in the RAK831 Pilot Gateway. If GPS is disabled, the GPS antenna does not need to be attached. Gateways usually do not change position, so its coordinates can be specified in the TTN console. In the packet forwarder software, you can configure if a real, fake, or no GPS is used. In the following slides, I will demonstrate how to enable GPS and set some beaconing parameters, in case you want to know how it is done. Note, I cannot offer you more information regarding Class B devices and beaconing. This is the Semtech GitHub page. To find beaconing parameters, select Packet Forwarder, select this folder, LoRa Packet Forward, and select folder CFG. And here is where I got my beaconing parameters from. I got the beaconing parameters from this file. I have used these beaconing parameters. Go to this folder, make a backup of your original local config.json file, and modify the local config.json file. Add these lines to enable GPS, and add these lines to set beaconing parameters, which I have explained earlier. This is what my local config.json file looks like after the changes. It is recommended to make changes in the local config.json file. If some parameters are defined in both global and local configuration files, the local definition overrides the global definition. Now place the GPS antenna outside with a clear view to the sky. If the GPS antenna is inside, the altitude information will be way off. Now reboot and log into the Raspberry Pi. Check the syslog and see if GPS is enabled and see beaconing information. Here are some logging from the syslog. Here you can see some beaconing information. And here you can see that GPS is enabled. It shows you the latitude, longitude, and altitude. I expected an altitude of 10 meters, but instead it shows an altitude of -3 meters. This was because I've placed my GPS antenna inside instead of outside. You can also read GPS data in NMEA format. Type in this command and you will see the GPS data in NMEA format. After this test, I have disabled GPS by restoring my original local configuration JSON file and detached the GPS antenna. Go to the Things Network and log in. Select Gateways. Select this link, Register Gateway. I have entered my gateway EUI. Check this box because the installed software uses the legacy Semtech packet forwarder. Enter a human-readable description. I have selected this frequency plan. If you select a frequency plan, it shows you the router this gateway will connect to. Find your gateway location on the map. Select the LoRa antenna placement. I've placed my antenna indoors. And press the Register Gateway button. Go back to the Things Network console. Again, select Gateways. This is the gateway I just registered. Select it. As you can see, the gateway is connected. Press Edit Location, and you can specify the altitude of the gateway in meters. Press the button Save Location. By default, the gateway Wi-Fi is disabled. Ethernet is preferred above Wi-Fi because you want to reduce additional radio signal noise inside the gateway enclosure. When you log into the Raspberry Pi, you see this message: Wi-Fi is disabled because the country is not set. To enable Wi-Fi, open the Raspberry Pi software configuration tool, enter this command, select localization options, select change Wi-Fi country. I am selecting the Netherlands. Press right arrow key, select finish, press enter. Go to this folder and edit file wpa_supplicant.conf. I will now add the following lines. Add these 4 lines and add your router SSID over here and your router password over here. Enter this command to shut down your Raspberry Pi. After you have entered the shutdown command, wait a few minutes and pull out the power adapter and the Ethernet cable. Wait a few seconds and power up the gateway. Your router will assign a new IP address to the gateway. Go back in this tutorial and watch how to get the gateway IP address. Check if you can still log in into the Raspberry Pi with the new IP address. Also check if the gateway is connected to the Things Network. Go to the Things Network console, select the RAK gateway and check its status. Check if it is still connected. If the RAK831 Pilot Gateway is up and running and the gateway is registered with the Things Network, you may want to conduct several tests. Test if the gateway can handle activation by personalization. Use the procedure demonstrated in tutorial 24. Test if the gateway can handle over-the-air activation. Use the procedure demonstrated in tutorial 25. And test if the gateway can handle uplink and downlink messages. Use the procedure demonstrated in tutorial 25. As explained in tutorial 7, if a gateway antenna is outside at a high location and there is a direct line of sight with an end device, then this gateway can receive signals from this end device over a large distance. But what if the gateway antenna is inside, approximately 10 meters above ground and surrounded by buildings? What will the range be? I conducted a simple test where I used 2 gateways, the RAK831 Pilot Gateway and the Things Gateway. Both gateways are designed for indoor usage. As an end device, I used a Things node and went to different locations and recorded the received signals from both gateways. In tutorial 27 is explained how to retrieve and store sensor data from the Things network. For the range test, both gateways were placed in front of a window, as you can see over here, separated 9 meters from each other, and both are located 10 meters above ground. These are the measure points, and the gateways are located here. All measure points starting with a Z means the end device was inside a building. This measure point means inside the building on the 2nd floor, on the 1st floor, on the ground floor, and this is the basement. Here are other measure points. The gateways are located here. Here are the last measure points. Again, the gateways are located here. Please note, measure point T is inside a bicycle tunnel. All recorded data can be found at this link. Here is the recorded data. All measure points can also be found in a shared Google map. See this link. This is the shared Google map with all the measure points. The gateway is located here. These are the end-device measure points outside a building. And these are the measure points inside a building. If the RAK831 Pilot Gateway is placed in front of a window, monitor the gateway temperature, especially in the summer period with high ambient temperature and when there is direct sunlight on the gateway. To monitor the Raspberry Pi CPU core temperature, enter this command, and this is the Raspberry Pi CPU core temperature. It is recommended to keep the RAK831 Pilot Gateway operating temperature between 0 degrees Celsius to 70 degrees Celsius. Here are the RSSI measurements for both gateways at different locations. The end device is near the gateways, the end device is on the first floor, the end device is on the ground floor, and the end device is in the basement. Sometimes the gateway didn't receive the signal, as you can see over here. Here, and here. This is where the end device is in the bicycle tunnel. I hope that these range tests give you a realistic picture of the actual gateway range when you place the gateway antenna in a building at a height of about 10 meters and the gateway is surrounded by buildings. After carrying out these range tests, I conclude that in my case, both gateways have a range of about 520 meters. Please note, this is not a scientific test. It is just a simple test to give me an idea of the possible range of my gateways. To increase the gateway range, if you can, 1. Place the gateway antenna outside. 2. Place the gateway antenna as high as possible. And 3. Have a direct line of sight with the end device. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them.